Hi everybody, this is Dr. Nigro for a screencast for our Chem calculations in our equilibrium unit. This particular screencast is going to deal with the equilibrium expression, the equilibrium constant, and how we can use those things to solve different problem types. All right, so the equilibrium expression is a ratio of products versus reactants for a reversible reaction at equilibrium. All right, remember, there are a couple requirements for a system to be at equilibrium. The first is that the concentration of the reactants and products must be constant, and that the rate of the forward and the rate of the reverse reaction must be equal. All right, if we have those two conditions met for a reversible reaction in a closed system, then we say that that particular reaction is at equilibrium. All right, when that happens, that equilibrium is dynamic, which means that even though it doesn't appear that we have changes going on within our reaction system, the forward and the reverse reactions are actually still occurring. And so what we do is we look at those portions of our reactants and products that are still actively participating in the reaction, and we set up a ratio called the KEQ. All right, so our equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants. All right, and so it's always going to be products over reactants when we talk about KEQ. All right, now there are a couple requirements when we put together this equilibrium expression. All right, one, any coefficients from our balanced reaction become exponents in our KEQ expression. So if you have a particular reaction and we've got a coefficient of 2 in front of, say, hydrogen gas, then it becomes a square in our KEQ expression. All right. The second requirement, you can only include compounds that are gases or aqueous, in other words, a solution, when putting together our KEQ expression. All right. The reason for that is when we have liquids and solids, when they change forming reactants or products, their overall concentration remains the same. All right. So we don't include those in our KEQ expressions. All right. Third, that KEQ value is temperature dependent. All right, it doesn't really affect how we write our KQ expression, but it does impact the calculation. Now, you're going to see the temperature, or you should see the temperature listed with any problem dealing with the equilibrium expression. If it's not there, it's okay. It should be there, but don't worry. Some of the problems, there's typos. However, if you have the same reaction under two different temperature values, occurring under two different temperature values, then the KEQ values may be very different. All right, and that's okay too. All right. Now, once we talk about writing this, we can actually use that KEQ value to get an idea of what the ratio is at equilibrium in terms of products to reactants. All right, so what does that mean? Well, let's say, if we think about it numerically, let's say that your KEQ value is greater than 1. All right, so then if we think about our ratio of products to reactants, if we have a KEQ value greater than 1, then we must have more products present than reactants. So the amount of products must be greater than the amount of reactants present at equilibrium. All right. If instead our KEQ value is less than 1, all right, then we have the opposite situation. The denominator of our KEQ expression must be greater than the numerator. So the amount of reactants must be greater than the amount of products. All right. And then finally, under certain situations, we may find that KEQ equals 1. All right, and when this happens, that's okay. It just means that the amount of products is equal to the amount of reactants that are present. All right. Now, the amount, this word amount, is important because it determines how we incorporate this into our KEQ expression. We use these brackets like this, and that means molarity. All right, so we want to include our amounts of reactants and products. They have to be in terms of molarity, which means moles per liter. All right, so no grams, no just moles. We need moles per liter. Okay? All right, so with that in mind, let's write a couple KQ expressions. I've got a couple down here to work on. All right, so we've got KEQ equals, right? Remember, it's products over reactants. So we'll have HCl. It's got a coefficient of 2, so it gets a power. And then we've got H2 times Cl2. All right, so if we look at our expression, we've got all three are gases, so they can all go in. We have one coefficient, which becomes a power. And then we multiply our two reactants. All right, so it's multiplication, not addition. Keep that in mind as well. All right, so let's look down. We'll slide down to the next reaction. So KEQ equals, again, products over reactants. Now, if you look, we've got a liquid here, and that cannot go into our KEQ expression. So we X that out. And the remaining product is O2. There's no coefficient, so we leave it as a 1. And then we've got an aqueous solution, so that can go in, H2O2, and it has a power of 2. A coefficient of 2, so we get a power of 2. All right, slide up to our next one. We look, now this time we've got a solid. All right, that's also not allowed in our KEQ expression. All right, so all we have here are reactants. So it's going to be NH3 times the concentration of HCl. Right, and that's okay. Right, you don't have to have a denominator. It's fine, just like sometimes you may find that both products are liquids or solids, and if that's the case, you just put a 1 up there. And then our last one, we've got a KEQ value of O3, ozone squared, divided by oxygen gas, O2 cubed. So that would be our KEQ expression there. All right, so those are just a couple examples of how to write the KEQ expression. Please make sure that you use balanced reactions. All right, if the reaction is not balanced, then you're going to be out of luck. All right, you might be okay if they're all ones, but if they're not, then you're going to miss your powers. All right, so now let's try a problem where we actually use the KEQ, or in this case, rather, we're going to calculate that KEQ. So we have a reaction, and we're told that an equilibrium mixture at 425 degrees Celsius is found to consist of 0.183 molar H2, 0.313 molar I2, and 1.77 molar HI. Use this information in the reaction below to calculate the KEQ value. All right, so we check. We've got a gas, a gas, and a gas. Everything's balanced. So we start by putting our KEQ value in. So we've got HI squared divided by H2 times I2. All right, now we're going to plug our values in. Up top, 1.77 molar squared divided by 0.183 molar times 0.313 molar. All right, so we've got all our molarity values in. We have our square up top to match the coefficient, and then we're going to multiply the two below, plug everything into our calculator, and we find that our KEQ for this reaction is 54.7. All right, now I like to ask myself if that's reasonable. All right, that helps me catch some calculation errors. Here, KEQ is greater than 1, which tells me that I should have more products than reactants at equilibrium. If we look, I have 1.77 molar product compared to 1.183 or 0.313. So that is definitely the case here. All right, so this is an example of how to write out your expression, plug in your equilibrium values, and solve. All right, so let's try another one that's very similar. All right, an equilibrium mixture at 425 degrees Celsius consists of 0.12 molar HCl, 0.038 molar O2, 5.8 molar H2O, and 5.8 molar Cl2. All right, using this information, the reaction below, calculate KEQ. All right, so we check. We've got gas, 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 gas. So everything's going to go in. I'm going to check and see if it's balanced. 4 hydrogens, 4 hydrogens, 4 chlorines, 4 chlorines, 2 oxygens, 2 oxygens. So we're balanced, and everything can go into that expression. So KEQ is going to equal the concentration of Cl2 squared times the concentration of H2O squared divided by the concentration of HCl. I just saw an error here. I'll fix it in just a minute. Times the concentration of O2. All right, who can tell me what the error is? This is what I would ask my class. The error is here. All right. This is a gas. So its concentration, well, no, I guess it's going to be okay. It's just concentration is moles of the substance per liter. And for a gas, it's a little bit different than we talk about a solution. So even though you might say, well, how can I have a molarity for water? Right? Because it's a gas, you can do it. All right, so we're going to leave it as is. All right, now we're going to plug everything in. We've got Cl2's concentration is 5.8 molar. All right, we're going to square that times H2O's concentration, which is also 5.8 molar. We're going to square that too. Then we're going to divide that by the concentration of HCl, which is 0.12 molar. Raise that to the fourth power, and then the concentration of O2, which is 0.038 molar. All right, now you have to be friends with the calculator. You got to find that caret so that you can take this one on the bottom to the power of 4. All right, but in the end, you should get 1.44 times 10 to the 8th as our KEQ value. All right, now you might ask, well, what's the unit here? Well, KEQ has no unit. So KEQ is unitless. All right, and we look to compare, so we've got KEQ not equal, sorry, is again greater than 1, which means the product amount should be greater than the reactant. And if we check, we've got 5.8 for product, small numbers for reactants, so that holds true. All right, very good. All right, for our last problem, at 450 degrees Celsius, the value of equilibrium constant for the following system is 0.00659. All right, if the concentration of ammonia equals 0.000123 molar, the concentration of H2 is 0.0275 molar at equilibrium, determine the concentration of N2 at equilibrium. All right, so in this case, we know the KEQ value, and we're asked to find one of the reaction components given all of the rest. All right, so we're going to check our reaction. We've got a gas, a gas, and a gas. We're checked for balancing, 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens. So everything's ready to go there. We're going to write out our KEQ expression. So we've got NH3 squared divided by N2 times H2 cubed. So there's our expression. All right, now this time we're going to list our KEQ value at 0.00659 and plug in what we do know, 0.000123 molar squared. That's our NH3 amount. And then for hydrogen, we know that the concentration there is 0.0275 molar. We're going to cube that, and it's going to be times our unknown, X, which is the concentration of H2. All right, so I'm going to cube the 0.2075 and then multiply it to the other side. And then I'm going to, oh no, I'm not going to do that. Sorry, mathematics. All right, I'm going to multiply both sides by X and then divide that KEQ value under there with H2. All right, and when I get all that done, I find that the concentration of N2, which is X, is 0.11 molar. All right, now if you want to check it, just plug it back into your KEQ expression with your other two values, and you should get that KEQ value. If you do not, then you've made a math error and you got to fix it. All right. All right, so those are some examples of how to write a KEQ expression and then how to use that expression either to find KEQ or to find an unknown amount of one of your reactants. Okay?